Hello again. Let's take another example, curve sketching, and again here's the general ideas I'm going to follow for this example. And now we wish to sketch the function x squared times the natural log of x. Now recall that the natural log function is only defined for positive values of x. So that means that we have to consider that restriction in our domain. Our domain is then x must be greater than 0. Can we find intercepts? Well, x squared, x cannot equal 0, but natural log x can equal 0 if x equals 1. Right? We know that natural log x equals 0 if implies then that x equals 1. So I do have an x-intercept at 1, 0. There can't be any symmetry to the curve considering the domain. And there's no... I'm not sure exactly what happens at x equals 0. So we might think, if we think about the natural log function, the natural log function has a vertical asymptote at x equals 0. But what about x squared natural log x? I'm not sure about that. And so to figure that out, what I need to actually do is calculate a limit. What's the limit as x approaches 0 on the right of x squared natural log x? Now, if we were to try a direct substitution, x squared would go to 0. Natural log x, as x approaches 0 on the right, would go to a negative infinity. And so that's an indeterminate form. 0 times an infinity is an indeterminate form. So we have to adjust this so we can apply L'Hopital's rule. So I'll rewrite this as the limit with x approaching 0 on the right, and I'll rewrite it as natural log x divided by 1 over x squared. And now this fits the form of an infinity over infinity, negative infinity over infinity. And so now I can apply L'Hopital's rule. And this would become the limit with x approaching 0 on the right of 1 over x divided by, now that's x to the negative second, so that would be negative 2 over x cubed. And so then this becomes the limit with x approaching 0 on the right. And if we apply a little bit of algebra, this is negative x squared over 2, which would then be 0. So the limit as x approaches 0 on the right is 0. So that means the curve approaches the point 0, 0 from the right. It is not an intercept. The curve does not actually hit that point. It just approaches the origin. So let me note that real quick. It approaches the origin. There will be an open point at the origin, not a solid point. So I'll mark that right away so I don't forget that. All right, let's analyze now using the derivative. F prime x using the product rule would be 2x natural log x plus x squared times 1 over x. And so then that is 2x natural log x plus x. And so then that is x times 2 natural log x plus 1. So then we have critical numbers at x equals 0. That would be a critical number. Or taking the 2 natural log x, well, wait a second, x equals 0 is not critical because it's not on the domain. Right? The domain is strictly greater than 0. 2 natural log x plus 1, setting that equal to 0. Natural log x is 1/2, negative 1/2. So then x is e to the negative 1/2. And that approximates as 0.607 approximately. So now if we set up our number line, starting at 0, and here's e to the negative 1/2, and if we test numbers that are less, that are between 0 and e to the negative 1/2, we would have a positive number, and then the 2 natural log x plus 1. If you try a number that is between 0 and 0.607, that factor will end up being negative. So this ends up being negative. And if we test a factor greater than 0.607, this will end up being a positive. So taking that together, we would then have that the function f is decreasing on 0 to 0.607, and f is increasing on 0.607 to infinity. And since the function is decreasing and then increasing, we know that f has a minimum. So there's a minimum at 0.607, and then substituting into that value into the function, 0.607 squared times the natural log of 0.607. I did this earlier on my calculator. It ends up being approximately negative 0.184. So there's my minimum on the curve. Now let's analyze using the second derivative, using the result of the first derivative, and I'll start from the form. Doesn't really matter which form I use, but I'll use the form that I'm highlighting here, and I'll calculate the derivative from the form that f prime of x is x times 2 natural log x plus 1. Then the second derivative would be 1 times 2 natural log x plus 1 plus x times 2 times 1 over x. So that's 2 natural log x plus 1 plus 2. So that's 2 natural log x plus 3. And then setting that equal to 0, then natural log x is negative 3/2, which means that x is e to the negative 3/2, which is approximately 0.223. So then, if we think of our number line for the domain, 0, and then we have the 0.223. And I know that 2 natural log x plus 3 is since natural log is increasing, then 2 natural log x plus 3 is increasing. So if we have an important number, if we have a 0 at 0.223, it must change from negative to positive as well. And you can find that out just through substitutions as well. So putting that together, I know that f is concave down on 0 to 0.223. F is concave up on 0.223 to infinity. And then I have an inflection point at 0.223, and then substituting that into the function x squared times the natural log x, it ends up being negative 0.075 approximately. We cannot take the limit to negative infinity. We can take the limit as x approaches infinity for x squared natural log x, and that'll go to infinity times infinity, which is infinity. So I know it's going to continue increasing to infinity as we move to the right. All right, putting all this information to get a general idea of the shape of the curve, we're going to compare the derivative and the second derivative. And let's see, we have 0, and then we had 0.223 and 0.609. So 0.223, 0.609, and let's see, we had that the first derivative was decreasing up until 0.607. No, sorry, the first derivative was negative until 0.607. So the first derivative is negative until 0.607, and then changes to positive. The second derivative was negative until 0.223, and then positive. So, over the first interval, the curve is decreasing in concave down, then decreasing in concave up, then increasing in concave up. Let's fill in the details. I've already noted the open point at the origin. We know that we have an x-intercept at 1, 0. So let's use a scale. Let's make, there's 1. I know I have a minimum at 0.607, negative 0.184. And then I have an inflection point at negative 0.075. I'm going to say that, here's my scale on the y-axis. This is negative 0.1. So 2 marks to negative 0.1, another 2 marks to negative 0.2. So then I have a minimum at 0.607, negative 0.184, 0.5, 0.6, negative 0.184. So here's my minimum, somewhere about there. I have an inflection point at negative 0.223. So 0.25, that's 0.25, so 0.223 is a little bit less. And then negative 0.075 is about here. There's my inflection point. It was decreasing in concave down, then decreasing in concave up, then increasing in concave up the rest of the way. There's a sketch of the curve. The function is x squared times the natural log of x.